to do the following. This is time equals 0. So it's a one-handed value. I can indicate what time equals 0 means with one hand. It's just time equals 0. Time equals 40 is also a one-handed value. But the time from 0 to 40, I can't really explain that without doing this. It's from time 0 to time 40, so it's a two-handed value. Understand? The 70 is also not one of these. 70 is one of these. It's how much the position changed from this time to this time. If you will do the one-handed versus two-handed, it really does help. So, question? Josh, you asked something, I'm not sure I answered it. No, that's right. Yeah, the ideal is that dt, let's actually, I'll do this, is dt this, or is dt this? Yeah, dt is one of these. It's just that it's very, very small. So ideally, dt is so short that the integral's value is perfect. But if you try to draw that, what you're going to get is a time interval that's really narrow, and you'll be multiplying by a velocity, so you get the area of a very, very narrow rectangle. But those narrow rectangles would fill the space between the velocity graph and the x-axis perfectly. So, other questions? Two for Josh. Cool. Okay, turn to item 3. Turn to item 3. Turn to item 3. So you can sit there. Rachel, if you prefer, you can sit up here. It's up to you. Okay, on item 3, there's just a little note. Read the note and wave at me if you have any sort of misunderstanding of what the note is saying. And then I'll give more, I'll say it differently. So read the note on item 3. So prior to A, there's a note. Read that note and then just wave if you have any sort of, I'd like to have me explain that differently. So. Need additional explanation as to what they're referring to by this note on item 3. So everybody do part A, go. Answer part A. Stop me if you want to talk. Raise your hand if you have this written on your paper, please. Who has this written down? points? You want me to talk about it? So, okay, warning, all eyes on the board, everybody. Okay, a common mistake is to slip into not thinking and write this. The integral of velocity is v of 40 subtract v of 0. So that's a common error. That's completely wrong. When we integrate velocity, we don't find how much the velocity changes. We find out how much the position changes. So we get s of 40 subtract s of 0. So don't ever do that. Questions? Here's one way to help you remember. Danica's chart again. If you have a formula for position, and you take the derivative of that formula, you end up with a formula for the velocity. If you have a formula for the velocity, and you find the integral of that formula, so you integrate, you don't find the position, but you do find the change in the position. So that's how derivatives and integrals interact. Question?
So like it gives you a read.
Yes. When you start with the formula for position, you have just a formula. Take the derivative, you get a new formula for velocity. If you know the velocity, and you integrate over some time period, you find the change in position. You find one of these for that time period. Please.
And if we were trying to find the at position 40, would we just switch the would we just switch the equation?
So 2 points for Chris. A really good question. Look. Okay, so the fundamental theorem is just, this equals this. So you can rearrange the theorem to find whatever you need. Read the name for me. So what Chris is saying is, well, if I want to, actually, back to Josh's comment, 2 points as well. Look at me. So the fundamental theorem is really versatile. If I want to find out, how different is the position now versus how the position was? I want to find the change in position. I want to find displacement. I want to find one of these. I just do the integral. The integral finds this, the change in position. But if I want to find one of these, like the position, I need to rearrange this. So maybe I want to find s of 40. Well, that's easy. Just add s of 0 to both sides. So just add this over here. So then you'll have an equation that says s of 0 plus the integral is s of 40. If that didn't click, I have something else I can show that might help. Are you good here?
Yeah, no.
Anybody else? But you could also rearrange by saying, what if I want to find s of 0? Well, that means I want to get this alone. So I'm going to add the s of 0 to this side, like this. But I really want to get this alone. So I'm going to take this entire integral and subtract it to that side. So you end up with this. I don't think I've ever seen the fundamental theorem used any other way. You either calculate displacement, you rearrange to calculate s of 40, or you rearrange to calculate s of 0. So, questions? Cool. So that's what we did here. We haven't discussed right Riemann sum, but I think you can use the concept. Well, you maybe talked about it a little bit based on your questions. I don't remember. Every class had slightly different questions. But if you just take what you have learned about...
Mr. Smith?
Yes?
Sophia Bills is being checked out.
Okay. You take what you learned about left Riemann sum and apply the same concept, you should be able to do part B here and part C. So go. Feel free to talk to each other. Feel free to stop me. If you think about how to do a left Riemann sum, the logic is exactly the same. First person in 2 years to find it does work. I just have to hear. Yeah, the worksheet there is should have been. Well, there's two things going on. One, when we approximate these, we're not necessarily finding exact numbers. There can be errors here that aren't really errors in the approximation. What I need to do to make that is if I tell you that this is 244, then the numbers will work for the left hand. Now they won't work for right if the approximation is different. So does that make sense?
Oh, it tells you them? Oh, it tells you them. Right? That'll be 22.
Yeah, so.
How do you use the so the numbers on the left where we start from 0, yeah, we're going to start from 0, like on it. So then you only do 0. So because the right and the right one's 5 from the right, it's also the
Okay, I'm so confused. I didn't even know. So wait, so define velocity though. How do we like find position?
yeah, so we're trying to find it's like 35 times 5.
Oh, so can we just let's see. Should we find from 0 to 20 and then from 0 to 35 and then the difference between those two and then minus something? Yeah, but it would be like well, no. That's what I'm saying. So do we go from to 20? We find what this is right here, and then we go from 0 to 35 and see what this is, and then we just minus those.
I don't even know.
So,
Okay. Are we starting at this?
Don't trust that. I don't know. Big as I've always done. Yeah. I was like 45.
the left one.
That's not bad. I'm just trying to
That's not what
You look up for a minute. Okay, having never done a right Riemann sum, plus only the second one we've done, I want to talk through it. Remember, this type of question often shows up on the written section, and so what you write actually counts more than your final answer often. So be careful what you write. Make sure every single time you have to calculate an integral on the AP test, make sure you write whatever integral you are calculating. because it is very common for them to give points for simply writing the integral. They don't give points every time, but they do it enough that you don't want to lose that point. So please raise your hand if you have this written on your page. Point. Next thing, look, come on. No one talk, everybody look at me. Look, a really common mistake is the following. You write down the integral, that's what you're going to calculate. And then people will put an integral sign right here. That's wrong. We're not integrating again. Like we are calculating the integral. And to integrate means to multiply repeatedly and then sum them up. So there's no integral sign there. Don't ever do that. Questions? Okay. Riemann sum, really easy. Look here. I'm supposed to take velocity and multiply by time. A thing that you should get used to doing is a little quick check. The velocity is miles per minute. This change in time will be some number of minutes. So these divide out. My final result will be in miles, which makes sense because when I integrate velocity, I get a change in position. So I'm just double checking to make sure my units work, because I get paid for the units. Plus it avoids mistakes. Okay, so come back up here. I go to the first subinterval. Okay, the words left and right are referring to the graph, not the table. Because I have seen AP questions where they'll give you a vertical table like this. And it's kind of hard to think of left and right on a table. So the words left and right refer to the graph. All right, I go to the first subinterval. And this time, because I'm doing a right Riemann sum, I pick the time that is on the right of the first subinterval. That time is 25. I'm going to find the velocity at that time. Multiplied by the change in time for that first subinterval, which is 5 minutes. Okay, you don't need me to talk more about that. Please.
Will you just repeat that?
2 points for Elena. So it all comes back to really looking at the integral. That's why you really want to write the integral so you can see what you're doing. So I've got to go from time 20 to 35. And rather than do the perfect integral, which would be to go each and every infinitesimal moment in time, I'm going to go in big chunks of time. So the time period was specified in the instructions because they said go from 20 to 35 in 3 subintervals of equal length. Good there? Good. So that means I've got to go to the first subinterval and I've got to find a velocity in that subinterval. Well, there's many to choose from, but because it's a right Riemann sum, I go to the very right of the subinterval, which is time equal 25, and I'm going to find the velocity at that time. So v of 25 means the velocity at time 25. And that value is going to be 2.4. Are you good there? Good work. Anybody else want me to talk more? Then you just repeat the process. Okay, to earn the point, you must either have this line in blue or this line in blue. You can't have both. You don't have to have both. And then you need to have a final result. Put it over here. Somebody, what's the result?
45.5
units of miles. Question, Sydney?
Wait, so for the units, I get that it's like miles over minute because of the V of t, and then I get that t is minutes, but why wait, what happened to the D?
Oh, awesome question. 2 points. So the symbol here really isn't D and then T. The symbol is dt. Like it's one symbol. And it means an infinitesimal difference in time. Like an infinitesimal amount of time. So it's like from a time here to a time here. And these two times are infinitesimally close. So dt is some amount of time. Therefore, because we're measuring time in minutes, dt has units of minutes. So it's not a time, it's an amount of time. Is that good? 2 points. Anyone else? Please.
If you started with 35 and then went to 30 and then went to 25, would that be wrong?
No, they'll give you credit because adding the order doesn't matter. I recommend against it. It does seem like people who do that, in some future problems, they make mistakes. So I wouldn't. 2 points.
Do we need the top one where it's like B 25, or can we just go straight to the 2.4 and 25?
So to get full credit, you have to write this. You have to write this number. On the calculator portion of the test, all answers must be correctly rounded to 3 or more decimals. So we'll always practice 3 just so it's easy to check with each other. This comes out clean, it's not rounded, so that's fine. You have to have this, you have to have miles. You have to have either this series of 3 computations or this series, but you don't have to have both. You can have both, you don't have to. 2 points. Anyone else? Please.
I did the thing where you started with like V of 35 first, and my logic was just like, because it's on the far right of the interval, I guess, I'd start there, but is that wrong?
Yeah, it's like I was saying to Zach, in the future it can cause some errors.
Okay.
Because the left and right doesn't mean start on the right and go this way.
Okay.
It literally means go to the first subinterval.
Okay.
No, you're fine. Thinking to go to the right makes, I understand why you would do that. There's nothing wrong with what you were thinking. It's just not quite what it means.
Okay.
It means start in the first subinterval and pick the value on the right of that
Okay.
subinterval.
That makes sense.
Please.
So if there's a left-handed sum, then would you start on the 20?
Yep. So, Zach and Sarah, this is partly why I want you not using that method, because for any Riemann sum, for any integral, you're trying to go from 20 to 35, not from 35 to 20.
Yeah.
So we start at 20 and we just pick the first subinterval. If it's a left Riemann sum, we pick the value that is most left in the subinterval. Right Riemann sum, pick the value that is most right in the subinterval. In a minute, you're going to do a midpoint Riemann sum. Midpoint means you pick the value that is in the middle of the subinterval. So, question? So look up. Well, look. If it's a midpoint Riemann sum, raise your hand, please. I'll pay the whole room. Look at the first subinterval. What is the time that is in the middle of the first subinterval? Hands, come on. What's the precise time that is the middle of the first subinterval, Mary? How many knew it? 22.5? 0.2 for Mary. Look at the table. Look at the table. Just say it out loud, please, yes or no. Is a velocity available in the table at a time of 22.5? Yes or no?
No.
Louder?
No.
Very good. Okay, so they won't ask you to do that. Like, they won't give a problem where the subinterval is defined in such a way that you can't find the middle. So they won't. They'll give a problem where you can find the middle. So, any questions? Cool. Part C says use the graph to illustrate what the right Riemann sum looks like. Remember, not every time, but often when you are computing an integral, you can equate the integral with area. Not always, but often. So here's what happens in this problem. For this first subinterval, we're picking this v of 25 is the velocity on the right side of the interval. That's this right here, the 2.4. And so we're basically taking this value, 2.4, and we're multiplying by 5. So we're finding this area. If the integral had been done perfectly, we would have found this area. So if we had been able to do the integral with a dt that is infinitesimal, we would have found the green area. Instead, we found the pink area. So our estimate for this first subinterval is definitely too low. They're going to ask you about that. They'll ask if your estimate is an over or underestimate. For this first subinterval, our estimate is an underestimate. The ideal computation would have found the area of the green. You want me to talk more about that? That's going to be on the AP test for sure. The idea of under versus overestimate. It's also in the buff packet later. So, please.
Is there a way to find that if you under or over without a graph? Without like graphing?
Hold on. Points for Elena. I would put this in your notebook. There won't be room in the buff packet. This is one of those concepts that, again, you can add to the list of, okay, if I make sense of this concept, remembering is pretty easy. If I don't make sense of it, memorizing is hard. If you have a function, we've been using velocity, so we'll use velocity. And that velocity function is increasing somehow. And you integrate that velocity over some interval. Okay? So you break it into two subintervals. If the velocity function is increasing and you do a left Riemann sum, well, you're going to go to the first subinterval. No, okay, this is the other reason why learning the graphical part is crucial, because it makes answering this question easy. Go to the first subinterval. We're doing a left Riemann sum. We look to the left of the first subinterval. We find the velocity on the left. And so we'll be calculating this velocity times this change in time. So we would be finding an underestimate. That's because the velocity is increasing. If the velocity were decreasing, and we did the same thing, something like that. 1 second, Josh. And we do a left Riemann sum. We go to the first subinterval, we pick the velocity on the left. So we're finding this area. Now we have an overestimate. So if v of t is increasing, and we do a left Riemann sum, we're finding an underestimate. But if v of t is decreasing, and we do a left Riemann sum, we're going to be finding an overestimate. Okay, I have a hard time memorizing that trick, so I don't ever try to teach you to memorize the rule. I try to teach you to understand graphically what's happening. Once you understand graphically, when I'm taking the AP test, I just draw a quick picture. Like if they, I just look at the picture. If they don't give me a picture, I just look at the clues and say, oh, v of t was increasing, now I can see it. Josh?
So if it were a right Riemann sum, like from red, in the end it would be as overestimated, right? Because you take its value up on the right side rather than it's just the left.
Yeah, everyone makes sense of what Josh is saying. That's the whole idea. It's not to memorize a trick, but make sense of it. I look at the first subinterval. If I'm doing a right Riemann sum, I go to the right-hand side, I find that velocity. So now I'm getting this velocity times this amount of time. So I'd be finding the brown area. That would be an overestimate. So a right Riemann sum would be over. That's how you should answer the over-underestimate question. Not by memorizing a rule, but by understanding what's happening and just think about it for a second. So, answer your question? There you go. Please.
What if, some of the subintervals are increasing and some are decreasing?
Awesome. 2 points for Charles. Take 3, actually 4. That's a really good question. Take 5. Okay. It's exactly what Charles noticed. Because of the complexity of thinking about whether my Riemann sum is an over or underestimate, if the graph I'm integrating is going up and down, I have never ever seen them ask that. They always have given situations where the graph is either strictly increasing, strictly decreasing. Good question. Anybody else? Cool. Other questions here? So finishing part C, you should have drawn, let's see, right-hand side, it should have looked like this. And then this. The drawing is really a critical part of being able to answer that over versus underestimate questions. So. Cool. I'll let you do 4 at home. I don't think you'll have any trouble with that. At least 4A and B you can do at home. Do 4C, go. Do 4C. Actually, 4C, D, and E. So do, I guess you can just do all of 4. The first part goes really fast. So do all of 4, go. Do all of 4. Sorry. Yeah, you kind of have to do part A and B to do the rest, so just do all 4. Yeah, it's a city. Now, the idea on B was to, so this is a great start, then this would be DT. And then they're asking if they, write an equation can be used to calculate. So they're asking if this is long. But this is an equation that can be used. This is wrong. All I did.
But I see what, yeah.
Yeah, that makes sense. Oh, wait a minute, this is not right in slope. This doesn't hurt. The integral of velocity is always equal to the change in the position from 1 to 0. So you can't it has to be these two subtracted.
I thought that would mean time. I thought that would mean time. No, not. Because if I use this alone.
So the idea is how do you do this is true. Subtract that so 0. That's the same as the integral. 0 to 40.
Oh, wait. You just used the, well, I think we
Sure. All you're talking about you want to get this alone. Well, what I would do is say this is negative. So to add this is your side.
Wait, so
So then you have this equation.
So 164 plus 39 because that's the position of 5.
That's a 5 position. Oh, yeah. So 164 plus 39. So then that's 2 or 3.
Just did it on my calculator.
It's like, dang, you're
So I thought we were going to use this equation to find time.
Yeah, that's
No, we're not, that's right. I thought it was a position.
So this would by position. One more step, but I should by position. Nowadays, you can say, oh, it's just subtract the integral to the other side. Subtract this negative. Yeah. Now we have a division.
So this is saying, but these can calculate either or differences, right? Yeah, okay, never mind. That makes sense. I was thinking you could only use like this one of them.
Okay, hey, look up. Who has this written on 4A? Who has this written on 4A? Point. Who has this written on 4B? Do you want to talk about it? Point. Abby?
I was just wondering if, if it gives you the value of S of 20 or S of 40, would it be okay if you plugged in the number for that?
Absolutely, absolutely.
Because that shows the same understanding.
Yeah, for sure. Absolutely. 2
And I was
points
just
for
wondering, otherwise, what would the point of giving you S of 40 equals 234 minus B?
Huh? No, well said. It's perfect. It's perfect. Anybody else? I don't have this written now. Let's do a little shortcut. What's the answer to the equation? That was pretty easy. What did S of 35 end up being? 200 how many?
3.
Who has this written on their paper? 2 points. I'm not showing the midpoint sum just to save a little time. Any questions, though? I can write it out if you need me to.
I'm just confused how we got
This one. So what I would have done first is this integral. So it says 3 subintervals of equal length and values from the table. So I'm going to go from 5 to 15, 15 to 25, and then 25 to 35. So 5 to 15, 15 to 25, 25 to 35. Good stuff. So doing a midpoint sum, I pick the first subinterval, find the time that is in the middle, which is 10. So I'm going to find V of 10. So V of 10 multiplied by dt for the first subinterval is also 10. So now you continue. Second subinterval, the time that is in the middle is 20. The dt for the first subinterval, the second subinterval is 10. So the third subinterval, the time that is in the middle is 30. See with that? So V of 10 is 9.5. Times 10. V of 20 is 4.5. V of 30 is 2.4. Now that I've written it, let's check. A warning again. On the written section of the test, you have to be really, really careful to make sure you're very precise in your writing, otherwise you do lose points. On the next test, what I'll end up doing is I have what's known as an extra credit grading party. Party's the wrong word. But I have people sign up, and they come after school, and literally, like, the room is full of people, and I pay a big amount of extra credit to have them help me grade tests. So the next test, you won't write your name on it, you'll just put your student number, so no one knows whose test is whose. And then if you come to the grading, like, you have to look very precisely and say, did they write exactly what I have written? And if they don't have exactly what's written, they don't get the point. Like, it's graded that carefully. So who has this integral written down? Okay. This is part C, point. You can have this blue line or this blue line or both. Who has that? Yeah. Point as well. So what's the number here, Han? What is it? Say the number. 95. 95? Units of miles?
Wait, no, it's 164.
Oh.
Oh, I thought you were adding it together.
Oh, my bad. My bad, Josh. Sorry. So the total is 164.
I thought you said just that.
I get you. Yeah. No, you're good. That was my mistake. How many have this? Hey, how many have this?
I got that.
Point. Okay. Questions? Anything? Oh, please.
So the answer that you got for C, that's not a specific point you can find on the graph, right? But the answer that you got for E is?
Awesome. All eyes up. 2 for 3. Take 5. Look. Sorry, good job. No, it's perfect. It's this thing again. This is one of these. Like it's showing the integrals. The integral's always one of these, right? Well, I can't say that because we don't use the integral for a lot of things. This integral is like a change in position. It's like how much did the position change? But this is a position. Is that what you meant?
Yeah.
So D, we would do this. We'd say S of 35 is equal to position at 5 plus the integral from 5 to 35. Who has this written on their page? 2 more questions. And again, you can put in the number here, it's fine. Same thing. So 164 plus 39. Is that right? That's your question. Still not. So we're trying to find, you think of it logically, at time 5 the plane is at a position of 39. During the next 30-minute time period, the plane's going to change its position to the right by 203. So it went from a position of, it's this kind of a thing. Here's the origin. The plane is at a location of 39. In the next 30 minutes, the plane's position will displace to the right 203 miles. So 203 miles more than 39. So that's why we're adding the 39 plus the 203. Not 39 plus the 160. I'm having a rough day. The displacement is 164. The plane is at 39. It displaces to the right 164 more miles. So 164 plus 39 is 203. Now the plane is at a location of 203. This displacement is the 169. Shoot. Josh, just talk really loud and then I'll make
So I had a question about like
Please.
D, on part D right there. I just flipped the order of it. I'm not sure if it would make a difference.
This way?
Yes.
No problem.
Okay.
Nope.
I just looked at the point.
Yeah, for sure.
On the,
Good. Please.
just a question. Will they ever give us this, like, they gave us a interval, will they ever give it to us where it's like, say like 5 and 10?
No, they won't. Okay, go to item 7, please. Whoa, that's frightening. That's cool, though. Do that again. It's mesmerizing. It's pretty soothing.
I don't even remember.
Like, so you got it just perfect.
I know, they kept going back and forth.
Like, you had it balanced nicely. Too much that time. It'll down back. Wow. That's cool.
Wait, whoa.
Woo! Make it crack.
Notice, oh really, hey look, this is cool. If you notice the distance between the edge of the jar and the binder, there's like the mass of the jar is big enough that is overcoming the friction of the table. So it's cool. It's not like that space between the space between the jar and the binder is not increasing hardly at all. So if we leave that all day long, it might eventually come to rest. Like it has to, because otherwise it's like the world's greatest energy producer, which it cannot be.
I thought we were solving
Cannot
this
be.
problem.
Never mind. Okay. Come back to here. That's cool. So the people on the video are like, what are they talking about? Had to be here, you know. So. The video only gets my voice and the magic words. Here we go. Okay, it says, use the, that's really cool. It says use the graph to illustrate.
You could put this as an experiment in jars.
I'm not really that curious. I gotta be honest, I'm not that curious. Although I will say that I have a. So when I was like, quick side story. It's kind of related to the job. So when I was like 10 years old, maybe 12, it was a long time ago for me. I had an uncle who worked in he was what was known as the water master for a big irrigation system in rural Idaho. So he had to manage, he was in charge of like repairing and maintaining big, huge pumps and 2 lakes and the pipes that came out of the lake and fed the whole valley for farmers and things. And so he lived on a property where there's just huge shops and just lots of equipment. And one day when we were visiting, he's like, hey, let me show you how to weld. And I didn't know how to weld, you know. And he spent like a half hour, he just kind of gave me a taste of it. And ever since I've been just like fascinated. So finally my kids, and Marin's laughing. So my kids are grown now. Like my youngest is a junior at Utah State. My 4 above that are married, and so we have a little bit more time at home, you know. So last year I just got this idea, like, I still think it would be super fascinating to know more about welding. So I bought a welder. It's really cool.
Well, they said waiting.
Like it is fascinating. Like you just, and I bought like a high-end, not a high-end welder, but like the most kind of versatile type of welding machine. And it's really cool. You have this like piece of steel, and you have this little torch, and like you can just watch the metal melt. Like it's really cool. Okay, moving on. But I don't play with jars, no. I do play with the welder. Okay, back, speak, calm down. Okay, look. It says use a graph to illustrate what a trapezoidal Riemann sum approximation of that integral with subintervals shown would look like. So a couple of new things here. One, instead of saying use subintervals of equal length, they are switching it up and they're just telling you the subintervals. They do that on the AP test. So I'm doing this integral, and part C is the integral. So let's jump to here for a minute. So start out the same. You write down the integral. What you do is you go to the first subinterval. So they said we're going to go from 0 to 20. So here I am at the first subinterval, 0 to 20. Okay, trapezoidal is an average of the left and the right. So you go to the first subinterval, and you go to the left-hand side of the first subinterval, and you find the velocity on the left-hand side. So that's why I wrote up here v of 0. Just wait if you need me to talk through that again. So it's just like midpoint left and right. You go to the first subinterval, except instead of picking the time that is most left, or the time that is most right, or the time that is in the middle, you actually pick the left and right. So I've written down v of 0. I also write down v of 20. I picked the velocity that was most left and most right. But you need to talk through that again? Please.
So we just need to memorize that when it says trapezoidal, we just pick the left and the right?
Yep. You add them together, and then you multiply that by 1/2. So points for the whole room. Raise your hand and tell me. If you take two velocities, you add them together, and then you multiply the result by 1/2, what have you computed with regard to those two velocities? Talk to each other, hands up, come on. Take two velocities, add them together, multiply the result by 1/2, what have you found with regard to the two velocities? Carson. Yes. Look. Look. Okay. So when you do a trapezoidal sum, hey, it's just like left, right, and midpoint. You go to the first subinterval, you pick the time that is most left and the time that is most right. You find the velocities at both times, and then you average those two velocities. Questions?
Is it always times 1/2?
Say again.
It's always times 1/2.
Let's have the whole room answer that. Raise your hand, please. Will it always be times 1/2? Hands up. Just think about it. You always go to the first subinterval. You always pick the time that is most left. You always pick the time that is most right. You get the velocities, like Calvin said, at both of those times, and then you multiply by 1/2. So Tori, is it always going to be 1/2?
Yes.
Yes. How many do it? 2 points. Yeah, because you're always averaging two things. Two for Josh. Anybody else? Cool. Then all you do is take that velocity. See, look here, look. This computation, this in green is one velocity. It is the average of the left and the right, but it's still just a velocity. And then you assume that the particle will have, in this case, a rocket, the particle will have that velocity for the entire time of the subinterval, just like we did with left, right, and midpoint. Ashley, please.
So do we need to write all that down, or can we just like look at the table and just like add 5 and 22 divide by 2 and then just use that? Or do we need to write all of it down?
Really good question. Everybody listen, everyone. On the written section of the test, you have to write it out. Yeah, because they say show the computations that lead to your answer. Now, Ashley, you do have a choice. You can write what I have in red up here, or you can write what I am writing here in red, but you do have to write it out. Like, they want to see that you're doing the trapezoidal stuff. So either one, but please, Sarah.
So you couldn't like find it like the first interval is like 9.5?
No, because they require the computations to be shown, you have to write it out. So it's a bit of a pain in that regard, but
Yeah.
easy point. So 2 points for Sarah and Ashley. What else? Question, Abby?
Wait, why are we writing this under D?
I couldn't hear you say it.
Why are we writing the you just don't have enough room, right?
Yeah, I just didn't have enough room. Sorry, it's not part D, I just didn't have room, sorry. Okay, questions about the trapezoidal so far? Okay, look up here again, look up. Okay, when we try to illustrate what the trapezoidal Riemann sum looks like, you go to the first subinterval, you draw the line on the left, that's the velocity on the left. You also draw the velocity on the right, so that's this. And then you connect them with a straight line. That's not very straight. Okay, it's called the trapezoidal sum because in this case, note the difference. Come on, focus. Note the difference. Instead of computing a rectangular area, which you do in left, right, and midpoint, you're actually computing a trapezoidal area, the green. So earlier today we talked about this idea. Elena asked the question, it was a really good question. We said, it was right here, we said if the function is increasing and we compute a left Riemann sum, we can graphically see that our Riemann sum is going to be an underestimate, right? Okay, if we're doing a trapezoidal, it deals with the concavity. So if the function we are integrating is concave down, and we're doing a trapezoidal sum, we're going to go to the first subinterval. We're going to pick the value on the left, then the value on the right. The area we end up computing will be a little bit less than the ideal. So our trapezoidal Riemann sum would be an underestimate when the function's concave down. If the function's concave up, it'll be an overestimate.
So you do the left and the right, and then you slide.
Mm-hmm. Yeah, you're forming a trapezoid with the left and right values. That was 7. You'll finish these at home. But general questions about trapezoid. Anything? Cool. Okay, go to item 8B. Okay, it says use the graph to estimate the time interval when the particle is speeding up. We did this before, but the particle only had a positive velocity. When the velocity becomes negative, it's a little different. Still not hard, but just different. If you look at this graph, from time 0 until about, 13 seconds according to the graph, the velocity is positive. So say it out loud, please. Is the particle moving right or left? Right. Good. You're going to have to set the jar because Calvin's falling asleep. Okay. His eyes are just going like that. So, look. Questions? Then from time 13 to about time 35, because the velocity is negative during that time, the particle is moving to the left. Questions? Okay. So you should have memorized already. The positive and negative of the velocity indicates direction of travel. Positive and negative indicates direction of travel. The number, it's actually called the magnitude, okay? The magnitude of the velocity indicates how fast we are traveling in that direction. So just look at the numbers. During this time, I'm going to the right, because my velocity is positive. But I'm going to call out the velocities. 3, 4, 5. So if I'm moving to the right, and my velocity-o-meter, speedometer, right, says 3, 4, 5, just answer please. Am I speeding? Am I speeding up or slowing down? Say it. Speeding up. Comfortable? Okay. Now my velocity is going to go 5, 4, 3, 2, 1, 0. So I'm slowing down, but I'm still going to the right. When my velocity becomes, Lauren is acting it out perfectly. I'm going to the right. I'm speeding. It's hard to act out actually, because it's hard to I have to do it this way. I have to say, okay, I'm going to start out speeding up, and then I will slow down. So initially I'm going like 3 feet every second. Then I'm going to change to going only 2 feet every second. Then I'm going to change to going only 1 foot every second. So I'm slowing down. Right here is when the particle stops. Now it's going to move to the left. Listen to the velocities. -1, -2, -3, -4. Is the particle speeding up or slowing down? Speeding up. It's just going to the left. Questions about that? Awesome. Okay. We need to look at 9C. Go to 9C, please. Okay, 9C says at time equal 8, is the particle moving away or towards the origin. So you'll do this at home, but I want to just make sure that understanding is good before you leave the room. to figure out what's happening at time equal 8, you are first going to use the same things you've been doing throughout the packet to figure out where is the particle at time equal 8. The particle is moving back and forth along a straight line. Here's the origin, location 0. You need to figure out at time equal 8, where is the particle located? What is the position of the particle? Well, there's only 3 possibilities. At time equal 8, the particle could be actually right at the origin. It doesn't mean the particle stopped. It could be just moving, and right at time 8, it's right there at the origin. Questions? That's one possibility. If at time equal 8, raise your hand to answer this, please. Feel free to talk to each other. If at time equal 8, the particle is right at the origin, would you answer if the particle is moving away from the origin, towards the origin, or neither? Hands up. Right at time equal 8, the particle is right at the origin. Raise your hand and tell me. Would you say to the grader, the particle is moving towards the origin at that time, the particle is moving away from the origin at that time, or neither? Hands up. Come on. What are you going to tell the grader? So at time equal 8, the particle is right at the origin, right there. At that moment, is the particle moving towards, away, or neither? Kylie?
Neither.
How many vote neither? 2 points. If at that exact moment, the particle is at the origin, it can't be moving towards or away at that moment. At that moment, it is at the origin. Now, I've never seen them ask that, but just in case. Are we good? Okay. Other option is, at time equal 8, particle's somewhere over here, meaning the particle's position will be a positive number. Or, it is possible at time equal 8, the position is negative, meaning the position is somewhere over here. Does anyone need me to talk more about that? Please.
Is the origin always 0?
So the word origin on the AP test always means you got this moving object. It's not the start, ever. Well, it can be, but don't think that. Origin does not mean start, unfortunately. It sounds like start, right? It doesn't mean start. It just means on this line along which the particle moves, that's our reference, location 0. Points? Anybody else? Okay, think about this one, talk to each other, raise your hand to answer it. If at time equal 8, the particle has a position here, what information do I need to figure out whether the particle is moving away or towards the origin at that moment? Talk to each other and raise your hand. Like if I know the particle has a positive position at time 8, so it's over here somewhere, what else must I know to figure out whether the particle is moving towards the origin or whether the particle is moving away from the origin? Hands up. Come on. This really isn't calculus, this is common sense. Just common sense. It means it's easy to remember. Hands up. What else do I need to know? Come on, hands. Here's where the particle is located. Carrie's great. Good job. Oh, no, she's no. She had her hand up. Look. The particle is over here. What else do I have to know to figure out whether the particle is going this way or this way? Like towards the origin or away from the origin? What else must I know? Be brave. Come on. There we go. Sydney. I have to know the velocity. Look at me. Who knew that? Point. 2 for Sydney. If the particle is right here at time 8, okay, and the particle has positive velocity, is the particle moving away or towards the origin? Say it. Away. Make sense? If the location is here at time 8, the velocity is positive, the particle is moving away from the origin. This is what I've been teaching you all year long, is the more you can just make sense of an idea, it becomes literally 100 times easier to remember. Like, that's not a hard concept. If I know where the particle is, I can find the particle's velocity, I can figure out whether the particle is moving towards or away from the origin. If you try to learn some fancy mathematical rule, it's hard to remember. Just think of the common sense idea. And then if it doesn't click, you just ask me and we talk about it some more until it does. We want to talk about that more. Please.
So when would it be moving away from the origin?
So you'll say it and then it will click better. So if the particle's here, to make the particle go this way towards the origin, does the velocity need to be positive or negative? Negative. So if the particle's here and I want to move away from the origin, my velocity needs to be positive.
But what if you're on like the left side?
It switches.
Then it would switch.
So if I'm here and I want to move towards the origin, do I want positive or negative velocity? Positive.
So is that like on like the negative of the graph?
So
Or where the
it all depends on whether we're talking velocity or position, but so I have to know where I'm located first. So I find that I'm here somewhere, maybe, I don't know, I'm just making this up. If at that moment my velocity, which I can find from this, turns out to be negative at that moment, then I would be moving away from the origin. Two more points. Okay, last thing for today. Go look at item 10. There's a note on item 10 that you will need. We talked about this a little bit previously. If the particle has both positive and negative velocity, then it is moving both left and right. We've shown that here. This chart, this graph of velocity shows from time 0 to time 13, particle's moving to the right. Now the particle's moving to the left until about time 37.5. Okay? So if the particle is going back and forth and we want to calculate total distance traveled, what we're going to do actually is instead of integrating velocity, when we integrate velocity, we find displacement. We find how much the position changes. If we integrate the absolute value of the velocity, we calculate total distance traveled. So when you go to do an integral using the absolute value of the velocity, the only thing that's different is, look here, when you write out the integral, like you're doing your Riemann sum approximation, like say this one here, you're going to have an additional item. You can't just write down the velocity, you have to find the absolute value of that velocity. That's how you find total distance traveled.
When it says subintervals indicated by the data in the table, that means it doesn't matter like that they're equal in length and that, right? So
Perfectly stated. Perfectly stated.
For random subintervals?
Yeah, because it says here start at 8. So time equal 8. Go to time equal 40 and use the subintervals as indicated by the table. So there's the first one indicated by the table, second, third, fourth. So the first subinterval is 12 seconds long. The second subinterval is 5 seconds long. The third subinterval is 7 seconds. Fourth is 8. You just use the table. Question? Please.
So when you're doing the total distance, you get the absolute value of like
Of the velocity.
Yeah, the velocity.
Just the velocity, yeah.
Will they ever reference like the absolute value of velocity as speed, or will it just always be absolute value of velocity?
I've never seen them reference it, but they will test you on it. Yeah, speed is the absolute value of the velocity, and they'll test you on that. 2 points. Anybody else? Okay, homework again. You're going to do honest effort to get through the buff packet. I'll ask about it on Thursday and pay extra credit for your efforts. So, good work. Yeah, you can use your calculator for this entire unit, so once you get into the habit of bringing it. So.